In this example, I'd like to actually look at sum and difference formulas when the values of alpha and beta are not given. So as we look at the example below, it says find the exact value of cosine, and then we have UC inverses on the inside. At first glance, this doesn't even look like a sum or difference formula, but when we consider it closer and think about what our notation means, it actually is. You see the cosine function on the outside, and then contained within the function, you see a sine inverse. Well, an inverse function actually means an angle. So we can think about sine inverse of 2/3 as being our angle alpha. The same thing for tangent inverse. Tangent inverse can be thought of as an angle. We'll call that angle beta. And then in the middle of this, you see a sign, which is plus. So we're actually going to think of this particular problem as I'm wanting to find the cosine of alpha plus beta. Now it turns out I don't need to actually know the angle measures for alpha and beta. The information that's given within the inverse functions is enough for me to be able to create triangles, and then from there find the desired values that I need. So let's kind of think of this as two separate situations for a minute. Okay, on the left-hand side, we have sine inverse equaling 2/3. Well, we can think about this as the sine of my value alpha is equal to 2/3, and I know sine is equal to the ratio of y over r. However, because it's actually sine inverse, we also know that our alpha is restricted from what we know about inverses to the interval from negative pi over 2 to pi over 2. So let's draw a triangle for a minute and see what this is going to act like. Because of the restriction on alpha, I can't consider quadrants 2 or quadrants 3. Because I have a positive value 2 over 3, that means my triangle is actually in quadrant 1. The y value being 2, the r value being 3. I know that for this triangle I can find the value of x by using Pythagorean theorem. So let's do that. We have x squared plus 2 squared equals 3 squared. And if I solve that, I get x equals either plus or minus square root of 5. In this case, because I'm in quadrant 1, it would be positive square root of 5. And so this is what I mean about, here is the angle alpha. I don't actually need to know that value of alpha, and I can see that I have an x, a y, and an r value for that particular triangle. That will eventually be all the information necessary to do this problem. We, however, need to also come over here and do the same thing for the tangent inverse. Tangent inverse equaling negative 3 over 4 actually means, remember here that I had associated beta with this particular function, so tangent of beta equals negative 3 over 4. Alright, on here, beta, from what we know about inverses, is restricted between negative pi over 2 and pi over 2, not including those endpoints. If we draw a triangle, okay, we can't consider quadrants 2 or 3. Tangent is negative, which actually means that my triangle needs to fall in quadrant 4. That being the case, the negative would be on the top, and the positive would be on the bottom, since this ratio is y over x. Okay, I'll label these. So I have negative 3 as my y, 4 as my x, and then I need to figure out what r is. Once again, use the Pythagorean theorem. Be careful on both sides of this line. I'm using x and y and r, but I'm using one for one triangle and then one for a different triangle. Okay, so in this case, I'll have that 4 squared plus negative 3 squared is r squared. I'll have r squared is equal to 25, which indicates that r will be the square root of 25, which is 5. And so I have, for each of these angles, even though I don't know what alpha and beta are, I have a triangle that represents those particular values. I'll actually want to copy these triangles down so that I can pull those out, that information I'm going to need, and I'm just going to clean this up a little bit. Let me copy down my original problem. My original problem was I need to find the exact value of cosine of sine inverse of 2 over 3 plus tangent inverse of negative 3 over 4. Let me also pull down the two triangles that I found. The first triangle that I found was in quadrant 1. We had that the sides were square root of 5 for x, 2 for y, and 3 for r. And that was for alpha, which we're considering to be this part. And then for the other triangle, that other triangle is actually in quadrant 4. For its sides, we had negative 3 as the y, 4 as the x, and then 5 as the r. We were saying that that triangle was beta. And this is what we were considering as beta. So first, let me rewrite cosine as simply cosine of alpha plus beta. Using our sum formula, this would be cosine of alpha times, and then when it's cosine, we use a mixture. We use consistent functions together, so it's cosine of alpha times cosine of beta. We use different signs here. Sine of alpha times sine of beta. And then here, this is what I mean by I don't need to know the values of alpha and beta, I just need to know the x, y's, and r's. Okay, in this case, for cosine of alpha, I look at my alpha picture I have up above, and I say, okay, on this one, what is the value of x? The value of x is the square root of 5. What's the value of r? 3. Cosine of beta, for this picture over here. Okay, what's the x value? 4. What's the r value? 5. Minus. Look back at alpha again. We're doing sine of alpha. What's the y value? 2. What's the r value? Square root of 5. Sine of beta. Look back at the beta picture. What's the y value? Negative 3. What's the r value? 5. Okay, and then simplify this and you'll have your answer. We'll have 4 square roots of 5 over 15. Now do notice in the second part we have a minus sign and then we have a negative, so that will actually turn to positive. And then we have 6 over 5 roots of 5. I believe I have a mistake. Let me see if I can correct myself. The mistake is actually right here. The sine of alpha, let's look back at alpha. The sine of alpha needs to be y over r. My mistake is in the denominator. That should actually be 2 over 3. And let me correct this down below. That would actually make this denominator 15. Okay, that was going to be ugly the way I had it. Now, from here, I'll have 4 roots of 5 plus 6. I have a common denominator. It's all over 15. Okay, now this answer is simplified completely. I have a common denominator. I don't need to rationalize anything in the denominator. There's also nothing in the numerator that would factor that would actually help me. I see I have a 4 and a 6 which share a common factor of 2, but there are no factors of 2 in the denominator that I could cancel that 2 with. So this would be my final answer.